For centuries, the night sky was a familiar canvas, its celestial bodies charting predictable paths, seemingly fixed in their grand cosmic ballet. Our solar system, as understood by scholars and stargazers alike, comprised 6 known planets orbiting the Sun: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. This was the cosmic order, an ancient truth etched into the very fabric of human understanding. But then, in the quiet gardens and bustling observatories of 18th and 19th century Europe, that perception was not merely challenged, it was shattered, not once, but twice, by worlds that refused to be easily seen or simply understood. The first seismic shift occurred in 1781, in the humble backyard of a German-born British musician and amateur astronomer named William Herschel. With his self-built, powerful telescope, a magnificent instrument by the standards of his time, Herschel was meticulously surveying the heavens, systematically cataloging stars and nebulae. On the 13th of March, as he swept his gaze across the constellation of Taurus, a peculiar object caught his eye. It moved, not like a star, which remains fixed relative to its neighbors, but with a slow, deliberate drift. He initially logged it as a comet, a common enough transient visitor to the inner solar system, and dutifully reported his findings. Yet, as astronomers across Europe observed this new comet over the following months, its orbital path proved stubbornly elliptical, far more circular than any known comet. The implications were staggering. Herschel had not found a fleeting visitor, but a new, permanent resident of our solar system. He had, with a single serendipitous observation, doubled the known radius of our cosmic neighborhood. Suddenly, the solar system extended twice as far as previously believed, a monumental leap from the orbit of Saturn to the vast unknown beyond. The scientific community, however, was not quick to embrace this revolutionary idea. The concept of a 7th planet was an affront to centuries of established astronomical dogma, a testament to how deeply ingrained beliefs can resist even the most undeniable evidence. It was a slow, sometimes grudging acceptance, revealing as much about the psychology of scientific resistance as it did about the object itself. Eventually, this distant, pale blue world would be christened Uranus. But the story of these reluctant giants had only just begun. The discovery of Uranus brought with it a new mystery. As astronomers precisely charted its path across the sky, they noticed something unsettling. Uranus was not following the orbit predicted by Isaac Newton's pristine laws of gravity. Its trajectory wobbled. It lagged behind or sped ahead of its calculated position, as if an unseen hand were subtly tugging at it. This orbital anomaly, though slight, was a profound challenge to the very foundation of Newtonian physics, or, more thrillingly, a clue to an undiscovered world. The 1940s dawned with an intellectual race underway, a high-stakes detective story played out not with magnifying glasses and footprints, but with logarithms and complex equations. 2 brilliant minds, separated by the English Channel, independently took up the challenge. In England, a young, prodigious Cambridge student named John Couch Adams began his calculations, meticulously working through the perturbations of Uranus's orbit to deduce the position of a phantom world. His work, though groundbreaking, struggled to gain immediate traction within the somewhat insular British astronomical establishment. Meanwhile, in France, The formidable Urbain Le Verrier, a celebrated mathematician, embarked on the same Herculean task. He, too, calculated the precise location of this hypothetical planet, driven by the same unwavering belief in the universality of gravity. The tension mounted. Leverrier's calculations, perhaps due to his more assertive presentation, resonated more strongly with the European scientific community. On the 23rd of September, 1846, Leverrier dispatched a letter to Johann Galle at the Berlin Observatory. The message was succinct. Point your telescope to this specific patch of sky, and you will find a new planet. That very night, with the ink barely dry on Leverrier's letter, Galle and his assistant Heinrich Louis d'Arrest did exactly as instructed. Within under an hour of beginning their search, a mere 60 minutes, they spotted it. A faint, star-like object not marked on any existing charts, positioned precisely where Leverrier had predicted. This was Neptune. Its discovery was not an accident, but a triumph of pure theoretical prediction, an undeniable validation of Newtonian physics, and a testament to the power of human intellect to reveal the unseen. From their very first moments in humanity's awareness, these distant, enigmatic worlds, Uranus and Neptune, have defied simple observation, demanding instead a deeper, more imaginative mode of scientific inquiry, hinting at mysteries that still challenge our understanding to this very day. And few mysteries in our solar system challenge our understanding quite like the bizarre orientation of Uranus. While its initial discovery in 1781 was a triumph of mathematics, the planet itself held a profound secret, one so peculiar it cried out for a cosmic crime scene investigation. This ice giant, unlike any other major body in our celestial neighborhood, spins on its side. Its rotational axis is tilted by a staggering 98 degrees relative to its orbital plane, making it appear to perpetually roll around the sun like a cosmic bowling ball. This extreme obliquity is not just an oddity, it is a lasting scar, a frozen record of an ancient, unimaginably violent cataclysm that reshaped an entire world and set it on a unique, solitary path through the cosmos. To unravel this 4-billion-year-old enigma, planetary scientists have turned to the digital realm, transforming complex physics into vivid, high-fidelity simulations. The leading suspect in this cosmic whodunit is the giant impactor hypothesis. Consider the sheer scale of what this theory proposes. Not merely a gentle nudge, but a full-scale planetary collision. Picture a protoplanet, a nascent world perhaps the size of our own Earth, hurtling through the early solar system. This wasn't merely a rock. This was a substantial, fully formed body, possessing its own internal heat and considerable gravitational pull, on an intercept course with a young, still-forming Uranus. The impact itself would have been an event of almost incomprehensible violence. A body with the mass of Earth, moving at tens of thousands of kilometers per hour, striking Uranus would generate energy equivalent to trillions upon trillions of megatons of TNT. The sheer force would have instantaneously vaporized vast quantities of rock and ice, tearing away immense portions of Uranus's nascent atmosphere and mantle. This wasn't a glancing blow. This was a direct head-on or near head-on collision, specifically aimed to deliver the rotational energy needed to flip a planet that is 14 times the mass of Earth onto its side. The immediate aftermath would have been a superheated, incandescent cloud of debris, a swirling maelstrom of vaporized elements and molten fragments. This material, flung out from the point of impact, would not escape the planet's powerful gravity, but would instead settle into a vast, flat disk encircling Uranus along its new, drastically tilted equator. This luminous, temporary ring of wreckage would have stretched for hundreds of thousands of kilometers, glowing with the residual heat of the collision, slowly expanding and swirling like a colossal cosmic hurricane. From this infernal, swirling crucible, new structures began to coalesce. The microscopic particles of rock and ice within the debris disk, cooled by the vacuum of space, would have gradually clumped together through gravitational attraction. Over millions of years, these fragments would have grown, gathering more material, until they formed the faint, dark rings we observe today, along with Uranus's tightly packed system of icy moons. Unlike the moons of Jupiter or Saturn, which are widely believed to have formed alongside their parent planets from the primordial solar nebula, Uranus's satellites are the children of this singular, cataclysmic event. They are not primordial companions, but rather the unique offspring of a cosmic collision that fundamentally altered their world. This ancient trauma, etched into Uranus's very being, transformed it from a mere planetary oddity into a dramatic survivor, forever bearing the scar of a formative event that set its evolutionary path dramatically apart from its gas giant cousins. Some secrets are written in the stars, but others are etched into the very orbits of planets and their moons. As the early solar system convulsed with gravitational turmoil, setting in motion the cataclysm that tilted Uranus onto its side, the ripples from that chaos may have extended far beyond a single world. They may have reached across the cosmic abyss, playing a pivotal role in the dramatic saga of Neptune and its largest moon, Triton. This world, a true enigma, reveals a story of cosmic theft, a tale woven from immense gravitational forces and the violent embrace of a distant giant. Examine Triton's very movement, and a profound anomaly immediately presents itself. Unlike virtually every other major moon in our solar system, Triton does not orbit Neptune in the same direction that Neptune rotates. Instead, it circles the giant planet in the opposite direction, a phenomenon known as a retrograde orbit. This retrograde motion is not merely an oddity. It is a dynamic impossibility for a moon that formed alongside its parent planet from the same swirling disk of primordial gas and dust. A moon born in such a way would always orbit in the same direction as its planet's spin, a fundamental law of celestial mechanics. This suggests Triton is no native, no primordial companion. It is an impostor, a trespasser from the distant, frigid Kuiper belt, the same remote reservoir of icy bodies from which the dwarf planet Pluto hails. The leading capture theory suggests that the same gravitational instabilities that sent a massive impactor hurtling towards Uranus in the early solar system could have also flung a binary pair of Kuiper belt objects into Neptune's path. Envision two icy worlds, perhaps each hundreds of kilometers across, locked in a delicate orbital dance around each other in the distant fringes of our solar system, their gravitational bond holding them together. As this binary pair was gravitationally perturbed and hurtled inward towards the inner solar system, it would have encountered the immense gravitational well of the forming Neptune. This celestial ballet of capture would have been a high-stakes gravitational drama. As the binary pair neared Neptune, the giant planet's immense gravitational pull, a force capable of bending space-time itself, would have torn them apart. One object, the now vanished partner, would have been flung from the system entirely, ejected at an incredible velocity, sent careening into the vastness of interstellar space, never to return. But its sacrifice was Triton's salvation. The momentum lost by the ejected partner allowed Triton to be snared, caught in a complex gravitational embrace, eventually settling into its bizarre retrograde orbit around Neptune. This violent capture was far from a gentle handshake. The immense gravitational forces exerted by Neptune during Triton's capture would have subjected its icy interior to an epoch of incredible tidal heating. For millions of years, Triton would have been squeezed and stretched, kneaded by Neptune's gravity like a cosmic stress ball, generating immense internal friction and heat. This internal furnace, a direct consequence of its traumatic capture, sculpted Triton into a world unlike any other, transforming its very geology. Its surface, observed in stunning detail by the Voyager 2 spacecraft during its flyby in 1989, appears bizarrely young, largely devoid of ancient impact craters, as if it has been recently resurfaced. Instead, it is a canvas of flowing nitrogen ice, marked by enigmatic cryovolcanic activity. Towering nitrogen geysers, plumes of superheated nitrogen gas, erupt hundreds of kilometers into space, then freeze and fall back as icy snow, constantly reshaping the Moon's landscape. These cryovolcanic eruptions and the bizarrely young surface make Triton one of the most geologically active bodies in the entire outer solar system, a testament to the enduring heat generated by its dramatic, violent capture. The stories of Uranus and Neptune, so far, have been tales of cosmic upheaval and mathematical triumph, of ancient impacts and stolen moons. But their deepest secrets are not etched on their surfaces or revealed by their peculiar orbits. To truly comprehend these enigmatic titans, we must plunge into their abyssal cores, to depths where the very laws of physics seem to bend, where matter itself takes on forms unimaginable to us on Earth. For within these cold, distant worlds lies a heart of darkness, a bizarre and dynamic realm unlike anything we have ever encountered. Peel back the swirling blue-green hazes of their atmospheres, descend past the crushing layers of hydrogen and helium, and you will arrive at a substance that utterly defies our everyday intuition. Here, kilometers beneath the visible clouds, we discover a vast, deep mantle of what scientists term ice. Yet this is not the frozen solid of a polar cap, nor the simple liquid of an ocean. This ice is something profoundly different, a hot, dense, soupy mixture of water, methane, and ammonia, existing under pressures that would instantly vaporize or solidify any material known to us on our home planet. The forces at play within these depths are staggering. Pressures there soar to levels hundreds of thousands, even millions of times greater than the crushing weight at the bottom of Earth's deepest oceans. Temperatures climb to several thousands of degrees Celsius, enough to melt rock and steel. These extreme conditions transform common molecules into exotic states of matter, pushing the boundaries of physics itself. For decades, this internal chemistry remained largely theoretical, a realm of mathematical models and educated guesses. Then, a breakthrough in laboratories on Earth began to illuminate this hidden world. Scientists, pushing the limits of experimental physics, managed to recreate these unimaginable conditions. At facilities like the renowned Lawrence Livermore National Laboratory, powerful lasers are focused onto tiny samples encased within diamond anvil cells, mimicking the immense pressures and temperatures found deep within Uranus and Neptune. Here, they have witnessed the birth of superionic water, a bizarre, transitional state of matter that is neither fully solid nor fully liquid. In this strange superionic state, the oxygen atoms, despite the searing heat, lock into a rigid crystalline lattice, forming a stable, solid framework. But within this solid cage, the hydrogen atoms, stripped of their electrons and reduced to positively charged ions, flow freely. They drift and rush through the fixed oxygen network like a fluid, behaving almost as if they were in a molten sea. This creates an electrically conductive, slush-like medium, a bizarre blend of solid and liquid properties, unlike anything found in the familiar inner solar system. This strange, conductive ocean of superionic slush is the true heart of these ice giants, the fundamental engine of their alien existence. Its unique properties are not merely a scientific curiosity. They are the key to unlocking some of the most profound secrets these worlds hold. It is this churning, electrically charged mantle, rather than a traditional metallic core, that we believe holds the answer to one of their most puzzling features: the origin of their mystifying magnetic fields. This exploration moves beyond our simplistic rock, ice, gas model of planetary interiors, presenting a vision of worlds that are far more alien, dynamic, and electrically charged than we ever imagined. What if the most fundamental tool of exploration, the compass, suddenly betrayed you? On Earth, its needle reliably points to our planet's magnetic north, a steady, unwavering guide derived from a colossal, self-generating field deep within our planet's metallic core. Yet, journey to the ice giants, Uranus and Neptune, and that familiar, comforting needle would embark on a truly bewildering, drunken walk across your dial, swinging wildly, its sense of direction utterly lost. This isn't just a quirky feature, it is one of the most bizarre and shocking revelations sent back by the intrepid Voyager 2 spacecraft. For decades, our understanding of planetary magnetism was built upon a relatively orderly model, exemplified by Earth, Jupiter, and Saturn. These worlds boast powerful magnetic fields, generated by what scientists call a dynamo effect, a complex interplay of convection currents within vast spinning oceans of molten, electrically conductive material, typically deep within their cores. Our homeworld, for instance, behaves largely like a giant bar magnet, its field tilted by a mere 11 degrees from its rotational axis, a predictable and relatively stable influence. Then, Voyager 2 made its historic flybys of Uranus in 1986 and Neptune in 1989, and the data that streamed back across billions of kilometers of space shattered these elegant preconceptions. The magnetic fields of Uranus and Neptune were, to put it mildly, chaotic. Scientists found that these planetary magnets were not centered on the planet's cores at all. Instead, they were dramatically offset, almost as if the entire magnetic source had been pushed to one side. Moreover, their tilts were extreme, utterly defying conventional models. Uranus's magnetic axis was found to be inclined at a staggering 59 degrees relative to its rotational axis, almost perpendicular to its spin. Neptune's field, while slightly less extreme, still tilted by a remarkable 47 degrees, a profound departure from the neat alignment of its gas giant cousins. How could two seemingly similar ice giants with their deep, strange interiors produce such wildly erratic magnetic fields? The answer, scientists now propose, lies precisely within that alien substance we explored earlier, the superionic slushy of their mantles. Unlike Earth, Jupiter, or Saturn, whose dynamos are thought to originate in deep metallic cores, the magnetic fields of Uranus and Neptune appear to be generated in a much shallower, thinner shell of this bizarre, electrically conductive superionic water. It is not the core that spins up the field, but a vast, churning ocean closer to the surface, a dynamic layer where oxygen atoms remain in a solid lattice while hydrogen ions flow freely like a liquid. This shallow dynamo model elegantly explains the perplexing observations from Voyager 2. Because the dynamo is generated in a relatively thin, convective shell rather than a massive, deep core, it is inherently less stable and more susceptible to local variations. This allows for the complex, multipolar nature of their fields, where magnetic lines emerge and re-enter the planet at multiple, unpredictable points, rather than a simple north and south pole. This also accounts for why the fields are so dramatically offset from the planet's center, as the churning, conductive region isn't uniformly distributed around a central core. Consider again the analogy of Earth's magnetic field as a simple bar magnet, a clean, bipolar force emanating from its center. Now, for the ice giants. Envision instead a messy jumble of shifting magnetic poles, like a dozen small, powerful magnets jostling within a thin, swirling soup, each pulling in a slightly different direction. This is why a compass on a hypothetical moon of Uranus or Neptune, or even on the surface of the planets themselves, would be a truly bewildering experience, its needles spinning erratically, unable to find a stable direction. The very physics governing magnetism seems to have been rewritten in the outer reaches of our solar system, challenging our deepest assumptions about how planets generate these invisible shields. In the vast, icy reaches of our solar system, a chilling paradox unfolds, challenging everything we might assume about distant worlds. You might expect that the farther a planet orbits from the blazing heart of our Sun, the colder it would become. Yet, when we turn our gaze to the ice giants, Uranus and Neptune, this simple logic breaks down, revealing a profound and baffling mystery of planetary thermodynamics. The data, meticulously gathered from billions of kilometers away, tells a story of two seemingly similar worlds that could not be more different in their thermal signatures. Neptune, positioned a staggering 4.5 billion kilometers from the Sun, is surprisingly warmer than its closer sibling. This blue behemoth radiates a remarkable 2.6 times more energy into space than it actually receives from the distant solar rays. It is as if Neptune possesses an internal furnace, a hidden engine of heat that defies its frigid surroundings. Scientists believe this warmth stems from the slow, ongoing process of gravitational contraction, a lingering heat source deep within its core, a primordial warmth left over from the planet's very formation, gradually leaking outwards into the vacuum. Think of it as a cosmic ember, still glowing faintly billions of years after its ignition, its enormous mass slowly settling, generating friction and heat as it does. But then, the cosmic thermometer swings to Uranus, a world that presents the exact opposite problem. Despite orbiting closer to the Sun, at roughly 2.8 billion kilometers, Uranus holds the dubious title of the coldest planet in our entire solar system. It radiates almost no excess heat at all, appearing thermally dead, a frozen anomaly in a universe brimming with dynamic energy. This isn't just a slight difference. It is a profound discrepancy, a scientific puzzle that demands a deeper understanding of these strange, water-rich giants. What could possibly explain this stark thermal contrast between two worlds that, at first glance, appear so alike? The answer, planetary scientists propose, might lie in the ancient, cataclysmic event we explored earlier, the cosmic crime scene that violently tilted Uranus onto its side. That colossal impact, which left Uranus spinning like a cosmic bowling ball, may have also fundamentally altered its internal structure and thermal evolution. We are not merely talking about a change in axial tilt. We are considering a trauma so profound it could have rewritten the planet's entire thermal destiny, freezing it into its present state of inert coldness. One leading theory suggests the collision was so unimaginably violent that it effectively blew away most of Uranus's primordial heat into space. Imagine an impactor the size of Earth slamming into the young Uranus, generating energy on a scale that beggars belief. This wouldn't just rearrange its orientation. It could have stripped away immense layers of atmosphere and outer mantle, carrying with them the nascent heat that should have been trapped within. This scenario paints a picture of a planet that, in its very infancy, underwent a thermal lobotomy, its internal engine catastrophically drained of its initial power. A competing hypothesis posits that the impact, rather than expelling heat, caused Uranus's interior to become stratified into distinct, non-mixing layers. Envision a planetary interior where the superionic slush of water, methane, and ammonia, instead of churning freely to transfer heat from the core to the surface, became locked into stable, separated strata. This layering would act like a cosmic insulator, trapping the remnant heat deep within the core, preventing it from convecting upwards and escaping into space. The planet would be warm at its very heart, but that heat would be permanently imprisoned, unable to reach the surface and warm the frigid atmosphere. This tale of two thermal profiles, one radiating excess heat and the other appearing almost utterly inert, highlights how two seemingly similar worlds, both born from the same primordial solar nebula, took drastically different evolutionary paths. Neptune retained its internal furnace, a testament to steady, unperturbed formation, while Uranus, scarred by its ancient trauma, may be eternally cold, a silent monument to a catastrophic past that continues to shape its present. How do we know any of this? How do we piece together the ancient traumas, the bizarre interiors, the wild magnetic fields of worlds so distant they are barely visible even through our most powerful Earth-based telescopes? The incredible insights we have gleaned about Uranus and Neptune, from their cosmic origins to their present-day enigmas, are built upon a foundation as fragile as it is profound. A fleeting glimpse, a mere handful of precious hours, provided by a single, audacious probe launched over 4 decades ago. This is the human story behind our understanding of the ice giants, a testament to ingenuity, dedication, and the relentless pursuit of knowledge at the very fringes of our solar system. In the late 1970s, a technological marvel began its epic journey. The Voyager 2 spacecraft, twin to Voyager 1, was a bold gamble on the grandest scale, designed to execute a grand tour of the outer solar system, a once-in-a-lifetime planetary alignment allowing it to slingshot from one gas giant to the next. For years, it delivered stunning images and data from Jupiter and Saturn, pushing the boundaries of our understanding with every passing moment. But its ultimate challenge, and humanity's longest wait for new worlds, lay billions of kilometers further out, in the frigid, uncharted territory of Uranus and Neptune. By 1986, after 9 years of relentless travel through the cold vacuum, Voyager 2 made its dramatic encounter with Uranus. It was a high-stakes moment, managed by the brilliant minds at NASA's Jet Propulsion Laboratory, a team led by visionary figures like project scientist Ed Stone. They had one chance, one pass, to gather every piece of information possible from a world that had previously been little more than a fuzzy blue-green dot. The probe sped past Uranus at speeds reaching over 70,000 kilometers per hour, a velocity that would take you from Los Angeles to New York in just 6 minutes. This meant that the entire period of intense data collection, the crucial window for observations that would define our understanding for generations, lasted only a few precious hours. 3 years later, in 1989, the stakes were even higher as Voyager 2 approached Neptune. This was its final planetary target, the last world on its celestial grand tour, before it would sail onward into the interstellar void. The team at JPL worked around the clock, making real-time decisions, calibrating instruments, and prioritizing targets for photography and measurement. Every command sent from Earth took over 4 hours to reach the spacecraft, and another 4 hours for the signal to return. It was an 80-year-old technology, a probe built in the 1970s, communicating across billions of kilometers, gathering data that would be irreplaceable. Scientists knew with absolute certainty that this single flyby might be humanity's only close look at Neptune for decades, perhaps even for a century or more, a stark reminder of the immense distances and logistical challenges of deep space exploration. The entirety of our modern understanding of these enigmatic ice giants, from their peculiar tilts to their mysterious internal heat, their chaotic magnetic fields to the peculiar orbits of their moons, rests almost entirely on this fragile foundation of aging data. It is a treasure trove, yes, but one meticulously collected during mere hours of close proximity. Decades after the flybys, scientists are still mining this data, scrutinizing every pixel, every radio signal, every magnetic field fluctuation. They are searching for what some call ghosts in the machine, subtle clues, unexamined patterns, and faint anomalies that hint at deeper mysteries yet to be solved, whispers from worlds still largely unknown. This ongoing quest, this patient unraveling of ancient data, reveals the profound limitations of our current knowledge. What we understand is merely what one probe, on one incredibly fast pass, managed to capture. It is like trying to comprehend an entire continent by flying over it in a jet airplane during a single sunrise. This highlights not just the desirability, but the absolute necessity of a return mission. The questions that remain, the clues that linger just beyond the reach of Voyager's sensors, demand a deeper, more sustained investigation, a second, more intimate look at the tilted worlds that guard the outer reaches of our solar home. The whispers from these ancient, enigmatic ice giants, those distant blue-green worlds, have echoed through our scientific halls for decades, urging us onward. After only the briefest of encounters, a mere flyby from a resilient 70-year-old probe, the call for a deeper understanding has become undeniable. Now, the scientific community has delivered its definitive answer. A dedicated mission to Uranus and Neptune is no longer a dream confined to the pages of science fiction. It is the highest priority, a flagship endeavor for NASA, formally recommended by the United States National Academies of Sciences' prestigious Planetary Science and Astrobiology Decadal Survey, a document that charts the course of space exploration for the next 10 years. This isn't just a vague aspiration. It is an ambitious, meticulously planned concept, a Uranus orbiter and probe. Its design is engineered to unravel the very mysteries we have painstakingly explored throughout this journey. Consider it humanity's most sophisticated deep space detective, built to not only visit, but to truly live with and understand a world that has guarded its secrets for billions of years. The plan is to embark on a voyage spanning over 2,800,000,000 kilometers, a distance so vast it would take a commercial jet flying at 900 kilometers per hour over 360 years to traverse. One of the mission's most audacious elements is an atmospheric probe, a small yet incredibly robust scientific marvel. This probe will be designed to plunge directly into Uranus's swirling frigid clouds, enduring pressures equivalent to a stack of 100 elephants standing on a single postage stamp. Its primary objective is to directly sample the planet's atmospheric composition and layered structure, gathering data that Voyager 2 could only hint at from afar. By precisely measuring the ratios of hydrogen, helium, methane, and heavier elements, scientists aim to reconstruct the primordial building blocks of Uranus, offering unparalleled insights into its violent formation and early evolution within the solar nebula. Meanwhile, the orbiter, the larger, more enduring component of the mission, will settle into a long-term, multi-year orbit around the giant. For years, it will meticulously map the planet's bizarre magnetic field, charting its wild, off-kilter dynamics with a precision impossible from Earth. This sustained observation will allow us to finally discern if the drunken walk of Uranus's compass is a chaotic permanent fixture, or if it shifts and evolves over time, providing crucial data for understanding the planet's unique shallow dynamo. Furthermore, through precise gravitational measurements, the orbiter will peel back the veiled layers of Uranus's interior, determining the exact distribution of its superionic slushy and whether the giant impact left it stratified, forever trapping its internal heat. The orbiter's scientific gaze will also extend beyond the planet itself, turning its instruments toward Uranus's enigmatic system of icy moons and dark rings. These are not merely celestial ornaments. They are the scattered children of that ancient cataclysmic impact, offering a fossilized record of the planet's violent past. Each moon, from the fractured surface of Miranda to the distant, irregular outer satellites, will be studied in unprecedented detail, revealing their composition, geological activity, and orbital dynamics. The faint, dark rings, barely discernible from Earth, will be mapped with a clarity that could unveil new, undiscovered ring features and the processes that shape them, perhaps providing further clues to the initial collision. This grand undertaking, now on the drawing board, frames our entire journey through the mysteries of Uranus and Neptune as a vital prequel to a real-world mission. These distant, tilted worlds are far more than mere objects of historical curiosity or eccentric oddities on the edge of our cosmic maps. They represent crucial missing pieces in the grand, overarching puzzle of how planetary systems, including our own dynamic home, form and evolve. They stand as cosmic laboratories, providing unique insights into the diversity of planetary architecture, helping us understand why our solar system looks the way it does, and what that implies for the countless exoplanetary systems we are now discovering across the galaxy. The answers locked within their bizarre magnetic fields, their frigid atmospheres, and their churning superionic hearts await. We have only just begun to truly comprehend these ice giants, these reluctant pioneers on the scientific frontier. A new era of exploration beckons, promising revelations that will redefine our place in the cosmos. The journey is far from over.